Um, Now it's final day. After 4 long days, there will be a final day, closing everything. So we have now learned the basic theory, really basic theory on single crystal X-ray diffraction, what happens with all these things, and you have already had an exam. We've been absolutely fine. There's some questions, of course, there related to work, what have been doing here. And now, yesterday we went through the idea how it really happens in real life with the program. So we were able to solve the structure, and we were able to see that, okay, everything is fine. So now we move to the final step, which is the analysis of the verification of the X-ray structure. And this is very important. This is at least important thing that growing a crystal is really having able to analyze what you have done. Because in many cases this can be misleading. That sometimes the X-rays are not telling you the real story. There might be an incorrect atom somewhere that, as you yesterday noticed, that the program was giving you something and it might not be correct. So you have to yourself see that it's chemically reasonable. These things happen sometimes that the X-ray diffraction, as it doesn't know the atom types, can give chemically incorrect answers, or then the computer program, like yesterday you noticed that it was calculated, I asked it to calculate hydrogen atoms, and in normal cases works perfectly, but sometimes this happens, it miscalculates something, so it's up to us to check that that is correct. And this is the idea. So the final this type of lecture is this 9, and then the 10 I will go and show you which kind of supramolecular structures we have been doing in the past 40, 30 years. So this is more, a little bit, and 10 will be more like a scientific discussion and a scientific talk, but not focusing on one topic like I did yesterday afternoon, but giving snapshots, different kind of things, what has been and can be done with X-rays. And some of them are really old ones. But let's go now in this analysis part. So what do we do after we have done the X-ray structure? So now the finalized X-ray structure, we are happy with this, is there. Everything has gone green. You can see here, all the atoms are correct. And now we know that these 3 peaks here are the background. We don't have to worry about them, so everything is fine. And now we have to do what we normally do. We do tables out of it. We call it crystallography tables. And now within this frame, there is a very simple and easy procedure to do this, because there is now tick a report, and when you tick the report, it will open up a sub-menu. This is the image here. And each of the individual abstract structures look into. So you can see here, collection, crystal, diffraction, absorption, publication, blah, blah. There's a lot of info here. But because it's a new structure, some of this is of course blank, we don't know it. But the point in there is that we want to have a full report out of it. And which will be in an HTML format, so we can open that in the browser. And that is something what we do. And it's very simple. When you have done it, in this report menu, which is now activated, as you can see, it's yellow, you click this Make Report. So this Make Report automatically reads everything what you have done. It reads a zip file, and it also extracts some other information which might be there. So it's a very nice tool. And now you can see we are now in this folder demo where we have all our files. Remember, we started from 2 files, and now it's about 10. And one of them is now the table file in the HTML format. And now, because we started with our structure name was demo, and now you can see that it says demo table. So that contains all these things. And you can easily open it with web browser, and it looks like this. So it really, this is a most important table in that sense. It indicates crystal data and structure refinement for demo. So for example, in previous years, this was always a part of a publication. So it was always published, it was part of a publication. But it disappeared some 10, 15 years ago when the zip file, you will soon see what is a zip file, that's the crystal information file which the program provides. When this came available, then it said, okay, you can find this information either from the SI or from the database. So typically this information now is given in SI. Depending on, sometimes you might report these also inside the paper, but typically it's not needed. So the most important is the crystal refinement data. And here what it tells us, name, the chemical composition, molecular weight, temperature, where it's done. Now crystal system orthorhombic space group, this is very important. Then the unit cell ABC, now all the angles are 90. And calculated volume, how many molecules of these we have in that unit cell, that's 4. And then from these information and the coordinates, it calculates density. So this is now the first time the density appears. So it's there. And this is, remember, the idea is mass over volume. That we can then calculate this density when we know all the atoms and atom types. And now this mu here, this is absorption coefficient, which tells us how strongly the atoms in this structure absorb X-rays. And this is not very important number, but in certain cases, if this number is big, let's say it's 50, 100 or even more, then it's normally indication that you should change the radiation. So it absorbs so much that given wavelength, like in this case it's copper, then it's okay, sometimes referee might say, okay, you have to do that with molybdenum radiation. But that's not so critical anymore, and the reason for this is that we can make absorption correction also with the new instruments for the copper radiation. So that is not so crucial anymore. Previously it was a value we lost. And then this F000 is actually the number of electrons in the unit cell. And that number, of course, indicates how many electrons, and it is an indication about also diffraction power, but also about the contents, what we have. So this number is actually 4 times the electrons of this, because we have 4 molecules in there. But it prints it out. This was, again, an important number, which is indicated 20 years ago. It has lost now its importance. It's not so important. So what are important is the unit cell, of course, and then the space group, and then the molecule itself. And then crystal size, we didn't indicate the crystal size, but this is crucial information. So when you are putting a report up or so on, you always have to measure the crystal. And in this case, it was not measured, we didn't have the information anywhere, so it gives a question mark on that. But the nice point in here is that you can edit this. So you can go there and then you have your notes, and the notes say that, okay, the crystal is 0.1 times 0.2 times 0.3, and then you type it there. And now you can see, which is also important information about the radiation. So it's a molybdenum radiation. This is information from the data collection. This means that what is the range of the reflections which have been collected. That's there. And now this gives now the index ranges to HKL. You can see H, K, and L. So it means that it has collected all information from minus 8, minus 12, minus 24, up to 9, 12, 25. And now if you look, there is a nice rule of thumb here. So if you look for, because H relates to the A-axis. And the A-axis is 7, but now here the A is bigger, it's minus 8 to 9. So it means that our resolution is then more than the length of this, so it's more than 1. And then if you look for the B, so it's 10, and here we go 12 to 12. and then in here it's 20, so here's 24, 25. So you can see always we aim that these H-scale ranges are bigger than their unit cell axis. So it means that then we have a higher resolution. If they would be the same, then it would be that it would be 1 ohms of resolution. In some cases it would be okay. But typically we aim for this. And this is how many reflections it has collected. And this is quite a lot. Remember when we saw a few of them, but it's a 7,695. And now they have been measured several times, the same thing. Remember there is 002 and 002. It measures 2 times. So when you take an average and look for independent reflections, it's about 1/2 of that. So that is the real number of reflections we are using for our structure. So it's more than 3,000 slices of the structure we have to have in order to get the structure. And we have to collect all of them, because if we don't, then the checking program, what you will see later on, will complain. They say, now there is something wrong. And then the referees or anybody who's reading this, an expert, says, now there is a mistake in the data collection with the diffractive. And now that's the idea. And then it gives you how many data you have, that's the number of those reflections. Restraints, we can have inside the program induce some restraints, so the sum parameter doesn't move, but in this case there is 0, and then this is the parameters. So the idea is that we have 9 parameters for each atom, each non-hydrogen atom. And this indicates that, okay, we have a reasonable amount. It's not a very big structure, only 210 parameters. But the point, if you look for the mathematical calculations, what it's doing, it is using all these 210 parameters in each of these reflections. So it's a huge calculation. It's really, I remember a time when we had a slow computers, actually not in the PCs. So this kind of a calculation, what I was doing, showing you yesterday, it took a second or so, took hours. Because it's a computer which is doing these calculations. There's a huge amount of calculations. But okay, that's the idea. The goodness of fit is just the fitting value, which should be 1 if everything is fine, around 1. If this is grossly out from 1, then that's a normal indication that there is something wrong in the data. And then the R values, remember, these are the values which tell us how well our model fits with the data, and this number should be as small as possible. There are 2 values, one which we cut the weak reflections out, so they only accept reflections which are higher than 2 sigma, which is a normal, and then we can have all of them. You can see that this number is always more than this number. But this number, there is no absolute value for the R values. It can be 2 or this kind of a thing, 0.02, or it can be 0.1, so 10%. And they are both good, because that is not the idea. The R value itself is not proof for that the structure is good, first of all. And then, this is also an important point. We have a largest difference peak or hole. It means what is there when all the atoms are taken out. So that's the background. And the background is really weak, so it's 0.14. And remember yesterday I told that hydrogen, if it would be there, would give 1. So we know that it can't be anything. And now, then there is an important point. Yesterday, remember we discussed about them when we started the thing that we have a racemic crystal, we know racemic compound, but we didn't know that it's optically pure. And the optical purity means that it has 2 options. If it crystallizes in a space group which is centrosymmetric, meaning that there's a mirror image of it, it's the same as left and right hand. So there has to be 50-50, left hand, 50-50, right hand. That's absolutely okay. It's very common, actually. And that's racemic, that's racemic. But if you dissolve this and put it in an enantiomer, you don't see the differences, because in an NMR, the enantiomers are the same. You can't see difference. But in the X-ray diffraction, if they are, if it's a pure enantiomer, then there's a difference. And now, this space group here, this P212 and 21, is so-called chiral space group, and there is no mirror image in that space group. And when this is the case, the program automatically makes a calculation. What does this mean actually in real life? Though I don't have a board here, but normally I do it in the blackboard. If you consider HKL, so 002, for example, and then you look for its, and the other half is zeros or a -2. So in a case when there is mirror image, they are the same, the numbers are the same. But then if it's not the case that there is not a mirror, also there is no mirror between these two numbers. So the 002 has a different number compared to 0 -2. And now this difference depends on many things, but in this essence it depends on the handedness of the molecule, what you have. And then we can use this separation, do a mathematical calculation, is it the left-handed one or the right-handed one, the molecule. And then this is used by comparing these, we call it Friedel pairs, so the normal 002 and 0 -2 are Friedel pairs, which should be equal, but in this case they are not. And we can use this difference to look, is it the left-handed or right-handed? And there is a parameter here, it's a lower part, it's called a Flack parameter, and this comes from the why it's called the Flack parameter, because it was an UK crystallographer called Howard Flack who actually designed this parameter. So it's a mathematical formula or process to calculate the differences from the data, from these not equal pairs. And this number here, it's been tuned so that it's 0 when you have the correct enantiomer and 1 when it's incorrect. So what it means is that if you do this calculation and you are finally there and then you get the Flack parameter of 1, it means that you have the wrong enantiomer. So what you have to do, you have to tell the computer program to reverse all the coordinates. It can be done. You don't have to change the crystal because it's that. Only the coordinate set has incorrect handedness. You just reverse it and then you have it, and then the number becomes 0. So that's the idea. If you are ever looking for structures of chiral molecules in the literature, so one always look for this Flack parameter that is 0, but that's not enough, because in addition, the number here in a bracket, which is the standard deviation of this value, is very important. Because if this standard deviation is big, then statistically we cannot trust the number. So that would be the case that even if it's 0, but the ESD is high, then the referee might say that, okay, I don't believe because it's so uncertain. In this case, we are very lucky because there's chlorine and fluorine atoms, where this separation of this 002 and 00 -2 is big. And the more heavier atoms we have, the more bigger are the differences. So it's very complicated. This calculation is very complicated if we have a hydrocarbon. But it can be done. In a very specific technique can be done so that we can also get the handedness of a hydrocarbon. But as I said, the X-ray diffraction based on the Flack parameter, based on the difference between the data, is the only experimental tool method where you can for sure say, okay, my molecule is left-handed, right-handed. Consider pharmaceuticals, for example. It's very important to know what enantiomer you have, and that's the case. And the Flack parameter is a correct absolute, we call it the correct absolute structure or configuration parameter. And now when we have a non-central symmetric space group, which means that there is no mirror image, the correct value should be close to 0 with the small ESD. And in here, it's 0.01 in brackets 2, which is a very good value. We know that within 99.5% certainty, it is 0. So then we trust that that's the case. That's the most important table because it contains all the information. And if you have this chiral molecule and non-centrocentric space group, you will get the flak parameter. But if it's not, then it doesn't appear because you can't calculate the flak parameter on a case when there's a mirror image. It's not calculated at all, so you don't have to worry about it. But then what it brings out, of course, and previously in, let's say, 20, 25 years ago, this was also printed in the publication. In the real publication, not in the SI. At that time there was no SI, so everything was printed in the manuscript. But this is the fractional coordinates and the thermal parameters for this. So chlorine, fluorine, so on, you can see the list is here. They are not in order, but they can be ordered also. But that's the idea, is that if you would have to write a report, normally it's not included in the report because it is in the zip file. And then also it makes a more accurate table on the anisotropic displacement parameter. Remember that the atom when we started was like a ball, but when we finalized it looks like an ellipsoid. And this is called the anisotropic displacement or thermal parameters, and these are just numbers, so you don't have to worry about this. But this is not at all important. It's printed, but you actually don't need that. But then there are two tables which are of importance, which comes automatically there. So these are the bond distances. So now we can see here that distance between this carbon and that carbon is it's chlorine, sorry, is 1.72742, and the standard deviation is 3. And now when you consider the accuracy, the length scale is 10 to the power of minus 10 meters. And now we have an error in the third digit here. It's extremely accurate information. So it's difficult to actually understand this because we are always on an Ohmström scale, and then we are roughly on 1 something. But Ohmström is 10 to the power of minus 10 meters. And then we have the error in here, so you can easily see that it's there. It's extremely accurate result. And now the idea is that by historical reasons, I don't know why, maybe that was the idea when there were not very accurate measurement devices. This ESD is indicated so-called 1 sigma level. And the 1 sigma level is 66%. And it's quite uncertain. So what you have to do if you want to study statistically the bond distances, you have to multiply this number by 3. And then you get the 3 sigma level, which is 99.5. And this you can do sometimes if you're doing an analysis, then okay, is there statistical differences between the bond distances or angles? Then you have to take this into account. But in the normal life, you don't worry, because it's always reported like this. And it's a historical reason. So the 3 sigma would be better nowadays because it would be more accurate. But of course it's easy to calculate. But that's the idea. In here you can see then fluorine carbon distance is about 1.35 roughly. And then there is O carbon, this is 1.4, this is an OH distance. And then we have here, again, one of the same fluorine carbon, 1.331. And you can see, even though it's the same bond, carbon-fluorine bond, it's never exactly the same. So you have been told probably in the course that benzene ring, the carbon-carbon distance is 1.39 and the angle is 120. But this is ideal, it's idealistic value. The real values always have errors in there. So it's never the same. Like in here, some of the distances should be the same. Like here we have, this is from the benzene ring. You can see there are values which are really different. But within this experimental error, they are the same. So the absolute value is not the same, but within the experimental error, they are the same. So this is what we can extract. We will extract a lot of information, but we have to also critically look into the information what we have. So that is printed here. We can see nitro group is clearly, so all nitrogen, all distances are clearly shorter than carbon-carbon or carbon-nitrogen bonds. Now in here we have another table which is actually coming from the coordinate. This is the angle table. You can see there are more of the angles than distances, of course, because we can have many of the angles. The distance is the same, but we can have an angle in this direction or that direction. And the same applies here. Look. But now the angle accuracy is much smaller. You can see it's now in a tenth of a degree. So the distance is much more accurate always than the angle. And the same applies here. This is 1 sigma. In real life, you should multiply that by 3 if you want to see the real differences. But anyway, in most of the cases, the angles are less accurate than the bond distances. And then the other, if you do a report, this kind of a thing, like my course is doing, they have to add this thing and show that, okay, yes, I have these things in there. And then it really adds additional things. It calculates the hydrogen atom coordinates, but this is really interesting because they were calculated. They are not determined, so we let the program to calculate. But this is also an old standard way of showing also the hydrogen atom coordinates, but of course this is not needed. We don't need to know the positions of hydrogens because they are calculated. Then it makes a short, this program makes a short additional summary, and you can actually use different versions of the data. You can see here, this is now the crystal data in this form. So it writes the same information in a chapter-wise, but the other was a table. So it's up to the person to always think about, okay, shall I make a table, or shall I write them in a chapter-wise? And that's the idea. So this is what the program prints as a report. We can look into. But where is this based? So the actual idea, where is the information, what we have gathered? And that is actually in there. When we did the final part of refinement, we clicked this ACTA there. The ACTA command induces that the program write a zip, so-called zip file. So this is zip file. It comes from so it's name.zip. So this is the ending for this. So where does it come from? It comes from crystallographic information file. And it has a different format. It has a certain format in this file. So it's been agreed, I think 25 years ago, it has been agreed how to do this. And the idea, that's an ASCII file. It's a normal editor. You don't need a Word or anything for this. You need just a typical ASCII word band or something like that, and you can go and edit the file and see what it contains. But there is, if you go to the Structural Database program site, you can find an NCIFR program. It's free. You can download it, and it's nothing more than an editor. So this is an opening for the NCIFR, and it uses this coloring code for this. So the blue ones are the format of the information in what we call the CIF language. So you can see it says, okay, when this is out of creation data. So this means that, okay, when the report was done, it was done in 2018, or the zip file. And then you can see there are last publication contact author address. So there could be my address there, and so on. So in here, it automatically says publication section references. This it automatically reads because it knows the program that has been used. And now, chemical name systematic, chemical formula moiety, chemical formula sum. So it's automatically inserted, and then the chemical formula weight. So it has, you can see, it has a certain format of indicating this. And if there is no information, then it appears as a question mark. But if you have this information, you can go and edit. You can type it there. Like there, it says publication contact author name. I would write here between these brackets, Karius. And I would be like the contact author for this. And this is how it goes. And then it comes here, it comes coordinates and all the other information is there. So what to do then? Because this is the thing what we have. We have finalized everything, but then we want to have the final. We have done the check by ourselves. We have seen the list of coordinates, and we have seen there are bond distances and angles and all these kind of things. I will then show, it's also shown here in a cartoon, but I will also show you when we are looking, we can use a program to analyze our structure visually. But this is the printed version, but you also do them visually. So the point in there, here you can see, this is the Chemistry database website, and you can see here that you can have an NC for Linux, Mac, or Windows version. So you can go there and do this. But the point is there that then when we have everything done, we are happy with this, we have to do one final check. And this is a must nowadays, that no structure will be accepted anywhere if this is not done. That should be the case. And this is so-called check CIF. So CIF file is the file, what we made. It's our file. And this check CIF is a program which is not sitting on your computer, it's sitting on a server of ICUR, International Union of Crystallography. So what you do, you submit your own CIF file to this place to do the check. So that is like an independent person, independent entity has checked your data. It's not okay that you say my data is okay. The idea is that this system makes it and it writes a report. This is really important. So the idea now, CheckCIF reports on the consistency and integrity of crystal structure determinations reported in the CIF format. It checks that its formal is correct, but if it's the total cheat, it cannot see it because it doesn't know what is the real structure. But it can see if there is something missing, if some parameters are not correct. If the person, for example, has edited the CIF file and added their incorrect information, either on purpose or without a purpose, this check will tell us. And that's the idea. And it prints out the report, so the idea, select your CIF file. So we will browse here and we will go and put it in. And then we can here control what it outputs. So it can output an HTML file so we can see it, or it can write directly a PDF. So this is a typical thing what we do. So we write the report as a PDF and then we keep it, and if we have to, we will send it to the reviewers. That okay, this is now done, everything is fine, that's it. And then there are different ways, how the validation is being done. And then finally, if there is something of wrong, I will show you soon. If there is something wrong, it automatically makes a complaint about this. Says that okay, now there is an error here. And you have two choices. Either you can try to remove the error, that there is something you can do, or if you cannot, you have to explain it. And this part here is an output validation response form. So we can have this there, and we can type, for example, okay, the data was bad, our crystal was really badly diffracted. So we tell already in there why we get this kind of data. And this is the idea. So what it does is going, and then it says this is now done. Here is the report, download, CheckCIF report. You click this, it downloads to you. But the point is that there is a warning which says this report is for guidance only if used as a part of a review procedure for publication. It should not replace an expertise of an experienced crystallographer. So even if you do this, it might be the case that there will be somebody who wants to get really even more deeper in your structure and see if there's any errors. But normally that will be enough. So that is there. We download that out from there and it looks like this. So I'd like here a CheckCIF, this is one other program, a CheckCIF report. And now it says structure factors, meaning the data has been checked too. So it's looking, okay, do you have anything funny on your data? Is something missing? There everything is correctly done, and then also looks that. And now that's the same warning as before, and now it starts to print the report. So it says data block is the name, and then it gives you how accurate the carbon-carbon bonds are about the wavelength. It gives you the unit cell and it's a temperature, and now it's making two things. It calculates theoretically from the information from the zip file. It calculates theoretically what it should be. So it says calculated report. This is the numbers what you have in your zip file, and this is what are the calculated ones. And in this case, the numbers are the same. You can see it goes up here are the same. Now here and now in here there is only difference. So you can see theta max, and theta min. This is mean okay, and number of reflections calculated is 3044, and we have collected 3036. So there is now actually 8 reflections missing. And 8 out of 3000 is nothing, and quite probably this is a technical issue from the instrument. So the instrument has not been able to measure these 8 ones, but this is not a big thing. If this is a big difference here, then the program will start give warnings. Now you have not done something correct, something is missing or is incorrect. So that is why this is important to do this report, to do that. And now run the checks if for a structure included, that this is for my students to do this kind of a thing, that once you have done it, you have your tables, and then you have the checks if, and when you have done your homework, you have to submit this in there. That's the idea. But now I'll briefly go, before we go to, I will also show you something about the chemical structural database, how we do this. But this is the molecular drawing program called Mercury. It's also freely available. That was what I said in the beginning. When you have your file from your structure, you can use this. There are other programs like Diamond or any other molecular visualizing programs. This Mercury is quite handy. So it works like this. That you go there and open, and then that's the structure. I will visualize this. I will show that. It's better for you to see. It looks very similar like inside this OLX, inside the computer. But in here we can start looking how molecular distances or bond distances and angles, or where are the other molecules and all these things. Make a packing plots and all these kind of things. That's a very simple thing. So we read here. Now, this is actually how to make an image. So if we want to make an image of this thing and put it in the report, there is a way of doing. So we can save an image, and we save this screen, what is here. And that's the idea. And then it appears like this. This is now the image in there. And now it's in JPEG, you can put it in the Word or something like this. But then you can also, inside this Mercury, you can ask it to look for the next molecules or hydrogen bonding. So there is a tick here, H bond, and then when you use it, it will show the atom where it thinks is hydrogen bonded. As you can see, there's a dotted line, but you can see there's an atom here, nitrogen, and there is an O atom here. So why is this? This is only that it looks the distances, it doesn't show them yet. But if you do this, when you click it, you can actually see that there are 2 molecules. There's a molecule here, and that is the hydrogen bond. I will demonstrate that also in real life. So it's from OH, nitrogen, is this thing. OO distance is 2.9, it's rather long, and the angle is 150. So it's not a very clear hydrogen bond, but it's there. And that's the end. And then, what you can do, I will show it also very easy to make a packing plot. So this is to show how the molecules pack. And that's the idea. In this, if you remember, in the molecule, or the table says how many molecules we have in a unit cell. And it says 4, and these are the 4 molecules in there. But now if you ask her how many molecules are in an asymmetric unit of this molecule, Because now we have 4 different coordinate sets. We have the original and then those which come from the symmetry. So there are 3 times 2 1-screw axes. So it creates, each of them creates 1 coordinate set. It means that there is 1 molecule and then 3 coming from symmetry. So this would be the asymmetric unit. So asymmetric unit contains 1 molecule only. The rest comes from symmetry. And then, okay, okay, now I jumped already, okay, that's what we will see, you will see later on. Now this Mercury version, what I have, because if you take it standalone, it doesn't have the chemistructural database included, you will see what is it later on, but my version has it, so it has here a list of structures, 1.3 million structures, and you can visualize each of them, and there is one is shown in here. And then there's a top menu, and we can do this, and then toolbar to set anything common, kind of setting display styles, colors, and all these things. And display area to show these structures. And this is the structure navigator, so in this case, if we are in a database, it contains the names of that. It also contains here, your structure will appear as one name, if there is no other structure. And now here we have this kind of a contacts menu buttons, which easily shows the other molecules. I will demonstrate that soon. And here we can also exclude hydrogens and all this kind of a thing. This is a little bit that, by doing, you learn how it works. And status bar tests can tell you some help messages if you. So it's very intuitive. It's a very easy program to use. All in all. But what is there? So the Mercury program leaves multiple formats. Most common are the res file. Remember, this is the results file from your refinement, your rack structure solution, and then you ask your program to write the zip file. So what is the difference? So that is it. The content, information content is the same. Remember, this looks something what you saw already there as an int file, and there are the coordinates, and now this is now the zip file. It's just information. You don't have to know what is actually inside, but you can see that the formats are different. So, and Mercury can read also XYZ files and other files too. So it's quite interesting in that sense. But now quite quickly I will go through chemistructural database. And the only difficulty with the chemistructural database is that it's not free of charge. So you have to have your institute, national institute license to use it, but I will show it you anyway because it's a very nice tool of checking if the structure is known. If somebody else did it, and when, and where. That you don't repeat the same thing, so you don't publish the same thing. This has been published 10 times already. Okay, I don't want to publish because it's already known. And referees often, like myself, often check. If somebody says, this is now the first time in the world, I said, I don't believe you. I'm checking from the chemistructural database. And it's used. This is an old picture, but now we are somewhere there that is something like 1.3 million, 1.4 million structures. And it contains everything except purely inorganics. So if you have a purely inorganic structure, it's not in a chemistructural database. They say that normally what you have to have is a carbon-hydrogen bond. But carbon is the essence, so you have this kind of a thing. For example, some metal, polyoxymetalloids are there, in many cases. But if it would be purely said carbon, nitrogen carbonate would not be there. And then how you sometimes might see it, it's called the ref code. This is that each of the entry, each of the structure have their own individual code. And this is what there are. There's organic, metal organic, non-polymeric, single component, multi-component, and this number now 1.35 million structures. And I will show you briefly, and I will maybe, if I have time enough, to demonstrate that also in point. So this is how it works. So when you click draw, this kind of a window appears. It's like a chem draw. So we click benzene ring there, and then click also C, and then C, and then click A, so you can see chem draw at hydrogen. So this is the idea. So if we do this in sequence, we get the benzene ring, then the two carbons, and then I draw this guy. Now it looks like an ethyl benzene, and this is the minimalistic thinking about ethyl benzene, because here, if we don't say any atoms, consider that there can be any atom. So now we have benzene ring in the ethyl chain. Now let's see how many we have these. Then now benzene ring can have any other substituent. So now we click here search, and when we do it, another window opens, and when we click here search, this thing happens. So it reads now, and we get 2,406 hits. Each are containing. Now you can see what we were looking for is the red area. But now, because we didn't say that what is here on these cases, it was looking all of them. And this is now the ref code here. So this Abadev is the name for this. So this is the search hit as a ref code. And the number of hits is indicated in there. And now search, what you have done is defined as red. But now, we saw that 2,406 is too much. We can't really get anything out of it, so we have to focus it. So I can go and edit this one here. We'll define a little bit more detailed research, because if your search is really broad, you get millions. Not millions, but hundreds or thousands. But if you make it more narrow, then you do. We override the existing one, click yes, redo this. So look, we added hydrogens. Now this is really a benzene. And now we do the search again. Click start now. It became interesting. Now it's 52. So only by defining that it's a benzene ring, we kicked out more than 2,350 structures. And now the idea is that now you can see what is ethyl benzene. Ethyl benzene is a solvent which is being trapped with the structure. This is the real structure. Now you can see it's a moth structure. It continues that direction and that direction there, and you can see there are 52 of them. And each of these cases, ethyl benzene, is a solvent. So with this we can study the structures and we can look for what it contains. Is there something else than our molecule? This is how it works. Now research goes from 52. Now you want to know who did this. And then you will go there and click the author. You can see here, this is the persons, this is the journal, this is all the numbers, 2010. And there, in many cases, it also knows, when you click it, you can get the journal directly. So this is a very nice tool of looking very similar structure to what you have done yourself. And then the author and journal details for this now. And then this is also there, it's mercury, the same mercury, but it's inside the chemical structural database, but it's not so efficient. I was now thinking about the idea that we can do now, where's the boss? Boss is not there. So we could now have a short break, like a 5-minute break now, and then I will show you a bit this mercury program and so on, before I go to the final examples of the structures, which would be then more like a scientific lecture. You will see a lot of structures and this kind of things. And then you can see these are the products of the X-ray. But let's do it now. Let's now have we don't go too far. So we have an hour break for 5 minutes, and then we continue at 1:30.